Welcome to our bioprocess engineering online tutorial on how to perform a cell culture kinetic analysis on Spreadsheet. Through the bioprocess engineering online tutorials, you learn the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, visit us at bioprocessdigital.com. You also learn how to use Spreadsheet software for key bioprocess engineering tasks, including analyzing experimental results, modeling and simulating bioreactors, designing and optimizing bioprocesses, evaluating economic and environmental performance. In this tutorial, you will use a spreadsheet to analyze the experimental kinetics of animal cells growth in a bioreactor. You will learn which growth and death rates need to be determined, how to numerically calculate these rates using a spreadsheet, how the growth and death rates change throughout the culture process. For this kinetic analysis, a Chinese hamster ovary, CHO cell, is grown in a laboratory bioreactor filled with 2 liters of medium at a controlled temperature of 37 degrees Celsius. The chemically defined serum-free medium contains an initial 60 millimolar glucose and 15 millimolar glutamine concentrations. During the culture, pH is maintained at 7 through addition of sodium hydroxide, and dissolved oxygen is controlled at 50% saturation through air and oxygen sparging. During the culture, medium samples are taken once per day and analyzed for the concentrations of living and dead cells using the trypan blue dye exclusion method. Cell concentrations are expressed in 10 to the 6th cells per milliliter or 10 to the 9th cells per liter. Starting with an inoculated cell concentration of 0.2 times 10 to the 9th cells per liter, the CHO cell culture undergoes growth over a 6-day period. After an initial rapid growth phase lasting 4 days, the growth slows, ultimately reaching a maximum viable cell density of nearly 4 billion cells per liter. Simultaneously, the concentration of dead cells increases, reaching up to 1.5 times 10 to the 9th cells per liter. After 4 days of culture, both cell growth and cell death occur simultaneously. To determine the actual cell growth rate, it is important to consider the total cell concentration produced during the culture. The total cell concentration, XT, is calculated as the sum of the measured viable cell concentration, XV, and the dead cell concentration, XD. The total cell concentration, XT, continuously increases over the 6-day period, indicating that cell growth is maintained throughout the final 2 days, despite the presence of cell death. When analyzing the kinetics of cell cultures, 2 types of rates are determined. First, the cellular specific rates. These rates characterize the metabolic activity of cells during the culture. For growing cells, the specific rates to determine are the specific rate of growth mu, measured in 10 to the 9th cells per 10 to the 9th cells and per day, or day minus 1, and the specific rate of cell death, Kd, measured in 10 to the 9th dead cells per 10 to the 9th viable cells and per day, or day minus 1. The second type of rates are the volumetric culture rates. These rates express the intensity of the culture process within the bioreactor. For cell cultures, the volumetric rates are the volumetric rate of cell growth, Rx third, measured in 10 to the 9th cells per liter per day. This rate is the product of the specific growth rate mu and the concentration of living cells XV, and the volumetric rate of cell death Rd third, measured in 10 to the 9th dead cells per liter per day. This rate is the product of the specific death rate, Kd, and the concentration of living cells, XV. The objective of the culture kinetic analysis is to calculate the volumetric and specific rates from the experimentally measured concentrations, and to determine how the specific and volumetric rates of cell growth and death change during the culture. How are the cellular rates calculated from the batch culture experimental results? In a first step, the volumetric rates of cell growth and death are determined from the experimentally measured time variations of living and dead cell concentrations using instantaneous mass balance relations for the living and dead cells. For a culture component, the instantaneous mass balance on the culture that expresses the fundamental principle of mass conservation at each instant is written as inlet rate plus or minus production rate equals outlet rate plus internal variation rate. The second production rate term is positive for the produced cells, negative for the disappearing cells. For a batch fermentation, there are no inlet rate and outlet rate terms, and the instantaneous balance simplifies to plus or minus production rate equals variation rate. Mass balance relations, typically expressed in grams of cells per hour or day, can also be expressed in cells per hour or day, assuming a constant cellular mass. The production rate terms in the balance equation involve both the positive cell growth rate and the negative cell death rate. The variation rate refers to the time derivative of the number of cells. For viable cells, the instantaneous balance for a culture medium of volume V can be written in 10 to the ninth cells per day as Vrx third minus Vrd third equals dVxV over dt, or Rex third minus Rd third equals dxV over dt. Accordingly, it is the difference between the volumetric rates of cell growth and death that determines the time variation of the viable cell concentration. For the dead cells, the instantaneous cell balance in 10 to the ninth cells per day is Vrd third equals dVxd over dt, or Rd third equals dxd over dt. Accordingly, at any time, the volumetric cell death rate Rd third is equal to the time variation of the dead cell concentration, thus equal to the slope of the tangent to the dead cell concentration variation curve. The specific death rate Kd is then calculated by dividing the volumetric rate Rd third by the viable cell density Xv. The total cell balance is obtained by adding the two previous viable and dead cells balance relations. This yields the relation Rx third equals dxv over dt plus dxd over dt, or Rx third equals dxt over dt. According to this relation, at any time, the volumetric growth rate Rx third is equal to the time derivative of the total cell concentration xt, which corresponds to the slope, to the tangent to the total cell concentration variation curve. The specific growth rate mu in day -1 is then calculated by dividing the volumetric rate Rx third by the viable cell density. The time derivatives of total cell concentration xt can be numerically calculated by fitting a curve through the experimental total cell concentration data. The observed time variation of cell concentration follows a sigmoidal shape, which can be effectively described by a fourth-order polynomial equation. Xt equals At to the power of 4 plus Bt cubed plus Ct square plus Dt plus E, where A, B, C, D, E are the curve fitting coefficients. From this curve equation, the derivative at any time is calculated as dxt over dt equals 4at cubed plus 3bt square plus 2ct plus d. The volumetric cell growth rate is then determined as Rx third equals dxt over dt. The steadily increasing concentration of dead cells over time is best described by a third-order polynomial curve expressed as xd equals bt cubed plus ct square plus dt plus e. From this curve equation, the derivative is calculated at any time as dxd over dt equals 3bt squared plus 2ct plus d. The volumetric cell death rate is determined as RD third equals dxd over dt. The cell kinetic analysis is carried out on a spreadsheet that contains the following sections: the experimental results table with the measured viable and dead cells concentrations during the culture, the cellular growth rates calculation section, and the cellular death rates calculation section. In the experimental results section, you first calculate the total cell concentration xt as the sum of the measured viable and dead cells concentrations. Graphically display the time variations of the viable, dead, and total cells concentrations. In the cellular growth rate section, you first determine the fourth-order polynomial curve that best fits the total cell concentration variation. The procedure is the following. Transfer from the above experimental results table the viable XV and total cell XT concentrations during the culture. On the XT versus time graph, add the trendline fourth-order polynomial curve through the experimental points and display the curve equation. Report the values of the polynomial coefficients A, B, C, and D. With these coefficients values, calculate the time derivative of the total cell concentration as dxt over dt equals 4at cubed plus 3bt squared plus 2ct plus d. Establish the formula at day 1 and copy-paste it to the following times. Set the volumetric growth rate Rx third equal to dxt over dt and graphically display the time variation of Rx third. Finally, calculate the specific growth rate mu equals Rx third divided by the viable cell concentration XV and graphically display the time variation of the specific growth rate. In the cell's death rate section, you proceed in a similar way to first determine the third-order polynomial curve that best fits the experimental dead cells concentration time variation. Transfer from the above experimental results table the viable cells XV and dead cells XD concentrations during the culture. On the graph, add the trendline third-order polynomial curve through the experimental dead cells concentration and display the curve equation. Report the values of the polynomial coefficients B, C, and D. With these coefficients values, calculate the time derivative of the dead cells concentration as dxd over dt equals 3bt squared plus 2ct plus d. Establish the formula at day 1 and copy-paste it to the following times. Set the volumetric cell death rate RD third equal to dxd over dt and graphically display the time variation of RD third. Finally, calculate the specific death rate as Kd equals RD third divided by the viable cell concentration and graphically display the time variation of Kd. Based on the observed time variations in CHO cell growth and death rates during batch culture, the following conclusions can be drawn about the kinetic characteristics of CHO cell culture. The specific cell growth rate is highest during the first 2 days and then gradually decreases over the course of the culture. The volumetric growth rate, which represents the overall intensity of the culture, follows a distinct trend. It increases, reaches a maximum around day 4, and then begins to decline. Since the volumetric growth rate is the product of the specific growth rate and the viable cell density, this difference in trends can be attributed to the increasing concentration of viable cells during the first 4 days. The rise in cell density compensates for the decreasing specific growth rate, causing the volumetric rate to continue increasing before it starts to drop after reaching its maximum. CHO cell death rates are negligible during the first 2 days of culture. After this initial phase, both the specific death rate and the volumetric death rate progressively increase until the end of the culture. How can these observed time variations be explained? The time variations in the specific rates of cell growth and death are directly influenced by changes in the culture medium composition throughout the batch process. Key factors include nutrient depletion. The gradual decline in glucose and glutamine concentrations limits cellular metabolism, leading to substrate limitation and a reduction in the specific growth rate. Metabolite accumulation. Simultaneously, the concentrations of metabolic byproducts such as lactate in ammonia increase over time. Elevated levels of these waste products inhibit cell growth and promote cell death, contributing to the rise in both specific and volumetric death rates during the later stages of the culture. Together, these factors create a progressively unfavorable environment for cell growth, leading to the observed variations in the growth and death rates. In this tutorial, you learned how to use a spreadsheet to analyze the kinetics of an animal cell culture. When examining cell culture kinetics, two key types of rates are typically determined. Cellular specific rates. They describe the metabolic activity of individual cells. Volumetric culture rates. They reflect the overall intensity of the culture process, influenced by both cell density and metabolic activity. These rates can be efficiently calculated in a spreadsheet using numerical derivatives of cell concentration variations over time. The investigated CHO cells culture is characterized by, for cellular growth, a decreasing specific rate, but increasing volumetric rate up to 4 days. For cellular death, negligible death during the 2 first days. Afterwards, increasing specific and volumetric cell death rates. If interested, you can gain a deeper insight in animal cells culture processes by enrolling to the online course, Animal Cells Bioreactors Principles. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more on our online tutorials and courses in bioprocess engineering. And be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.